Okay, so we will discuss today solid state, a new topic. So what is a crystal? So crystal as any solid material in which the component atoms are arranged in a definite pattern and whose surface regularity reflects its internal symmetry. So then we discuss laws of crystallography. The crystallography is based on three fundamental laws. What are those? First is Steno's law or law of constancy of interfacial angles. So this law states that angle between adjacent corresponding faces is interfacial angles of a crystal of a particular substance is always constant in spite of different shapes and sizes and mode of growth of crystal at constant temperature. Okay. So here you can see this is the angle is 90 degree, here also it is 90 degree, here also it is 90 degree. Next is law of rational indices. This law states that the ratio of intercepts of different faces of a crystal with the three axes are constant and can be expressed by rational numbers, that the intercepts of any face of a crystal along the crystallographic axis are either equal to unit intercepts, that is intercepts made by unit cell HKL, or some simple whole number multiples of them. Then Wise indices. In this method, the orientation of a plane is described in terms of the intercepts made by the plane on three crystallographic axes. The coefficients of A, B and C, here you can see coefficients of A, B and C are intercepts of the unit plane. Then the intercepts NA, NB and NC made by a plane are the integral multiple of ABC. The coefficients of A, B, C, that is N, N prime and N double prime, in this case are known as Wise indices of a plane. Then we discuss about a very important thing, Miller indices. Miller indices may be defined as the reciprocal of the coefficients of the intercepts of a face or Wise indices on the crystallographic axis expressed as integers. For example, let the plane intercepts all three axes at A, 2B and 3C, then Wise indices are A, 1, 2 and 3, like we just before we discussed. So it's multiple of A, B and C. Okay, so here NA, NB and NC, here N is 1 and N prime B and N prime C. So N prime is 2 and N double prime is 3. So Miller indices will be 1 by 1, 1 by 2 and 1 by 3. Okay, this is like your reciprocal of 1, 2 and 3. So if we multiply it by 6, so we get 6 is the, if we multiply it by 6, then we get 6 is to 3 is to 2. Second is A 3 beta alpha, so Wise indices are 1, 3 and A 3 B and infinity, so the Wise indices are 1, 3 and infinity. So the Miller indices are 1 by 1, 1 by 3 and 1 by infinity, so we get 1 is 1 by 3 and 0, so we get 3 is to 1 is to 0. Okay. Similarly, if we consider A minus 2B and 3C, so Wise indices will be 1 minus 2B and 3. So the Miller indices will be reciprocal of Wi or Wise indices, so it will be 1 by 1 minus 1 by 2 and 1 by 3. So we get 6 is to 3 is to 2. So we get 6, 3 bar and 2. So minus 3 we write 3 bar. Next we discuss Bragg's equation. The monochromatic radiation directed towards the sample produces constructive interference when condition satisfies Bragg's law. Okay, now for wave 1 and wave 2 to coincide, so this is our wave 1 and this is our wave 2. To coincide, the incident angle and the reflected angle need to be same. Wave 2 strikes on first plane at point A. Okay, so wave 2 here you see strikes at point A, and wave 1 strikes second plane at point B. So wave 1 traveled BC plus AD extra path. Okay, so BC plus BD. So BD here. Okay, so this is the extra path it is traveling, BC and then BD. For diffraction, this extra path should be an integral multiple of wavelength. We can say n lambda. Okay, so n lambda will be BC plus BD. So here you can see this is BC and this is BD. So n lambda will be BC plus BD. So n lambda equals to 2 BC, because as BC equals to BD here. Okay. Now if you consider triangle ABC, then so triangle ABC is this one. This is the triangle ABC. So if we consider triangle ABC, then BC by AB. So BC by AB. So AB is our D here. Okay. So if we write this one, so BC by AB is BC by D, where D is the interplanar distance. So you go there. So this is one plane, this is another plane. Okay, so this is the distance between the two atomic planes D. So this is the value of D here. So we write BC equals to 2D sin theta. Okay, or we can write n lambda equals to 2D sin theta. Okay, so BC will be D sin theta here. BC will be 2 sin theta, but if we consider this one, so n lambda is 2 BC. So BC will be here only sin theta, D sin theta, and then BC plus BD is nothing but 2 BC. Okay, so we write n lambda is 2D sin theta. So the above equation is called Bragg's equation. So this is the Bragg's equation here. Okay, this is the Bragg's equation. Now the distance between two planes. Okay, so if we write 1 by d square HKL equals to h square by a square plus k square by b square plus l square by c square, for a cubic lattice A, B and C, all three sides are the same. So we can write 1 by d square equals to h square by a square plus k square by a square plus l square by a square. So we get this expression DHKL is a by root over h square plus k square plus l square. So then we discuss law of constancy of symmetry. According to this law, all crystals of a substance have the same elements of symmetry, is plane of symmetry, axis of symmetry and center of symmetry. Now we discuss some basic definition of solids. So what is unit cell? The unit cell can be defined as the smallest three-dimensional repeating portion of space, that is, which when repeated over and again in different directions produces the complete crystal lattice. Then we discuss parameters of a unit cell. So its dimensions means lengths along the three edges as A, B and C. So these are the three axes here. Okay. So the dimension along these edges, three edges as A, B, C. So you can see this is A, this is B and this is C. Angles alpha, beta and gamma between the pair of edges. So these are the edges here. So this is one edge. Okay. So this angle is gamma. This is another edge. This angle is beta and this is another edge. This angle is alpha. Third point is characteristic of a crystal lattice. Each point in the crystal lattice is called lattice point or lattice sites. Each point in the crystal lattice represents one constituent particle that can be atom, ion or molecule. The three-dimensional arrangement of crystal points represents crystal lattice. Lattice points are joined by straight lines or bring out the geometry. Now, what are the types of crystals? On the basis of axial length ABC and the axial angles alpha, beta, gamma, we just discussed what is ABC, A, B, C and what is alpha, beta and gamma. The crystals are divided by 7 crystal systems or crystal habits. The characteristic of crystal systems are given in this table. First, if we consider cubic system, so in cubic system, so it's quite obvious that this is A equals to axial distance is A equals to B equals to C and the axial angles alpha equals to beta equals to gamma. So what are the possible variations for cubic lattice, like primitive, body centered and face centered? Example, NaCl, KCl, zinc blende, copper and silver. Then tetragonal. So possible variations are primitive and body centered. So in case of tetragonal, A equals to B but not equals to C, but alpha equals to beta equals to gamma equals to 90 degree. Examples are white tin, SnO2, TiO2, calcium sulfate. Third one is orthorhombic. So possible variations are primitive, body centered, face centered and end centered. So in case of orthorhombic, A not equals to B not equals to C, but here again alpha equals to beta equals to gamma equals to 90 degree. So all three angles are the same for cubic, tetragonal and orthorhombic. Okay, it's easy to remember. Now for cubic, axial distances are the same, A equals to B equals to C. For tetragonal, A equals to B but not equals B not equals to C. For orthorhombic, A, B, C all are different, value of A, B, C, but alpha, beta, gamma all are equal to 90 degree. So for these three systems, cubic, tetragonal and orthorhombic, axial angles are the same, but the axial distances they vary like this. So what are the examples of orthorhombic? So this is rhombic sulfur, KNO3, PbCO3 and BaSO4. Fourth is monoclinic, possible variation primitive and end center. So here A not equals to B not equals to C, but alpha equals to gamma here equals to 90 degree, but beta not equals to 90 degree. So monoclinic is monoclinic sulfur, example is monoclinic sulfur, PbCrO4, Na2SO4 dot 10H2. Next comes hexagonal, possible variation is primitive. So here A equals to B but not equals to C. Here alpha and beta are equal and they are equal to 90 degree, but gamma is 120 degree. Example graphite, ZNO, BeO, CDS. Sixth is rhombohedral or trigonal. Possible variation is primitive. Here A equals to B equals to C, alpha equals to beta but not equals to alpha equals to beta equals to gamma but not equals to 90 degree. Okay, all alpha, beta or gamma all three angles are the same, but they are not equals to 90 degree. That is the little difference. This is the difference from the cubic and rhombohedral or trigonal. In both cases, axial distances are the same, A equals to B equals to C, but axial angles are the same, alpha equals to beta equals to gamma, but for cubic alpha equals to beta equals to gamma equals to 90 degree, but here these angles are not 90 degree. Examples calcite or calcium carbonate, NaNO3, cinnabar or AgS, quartz and antimony Sb. And the last one, seventh one is triclinic. The possible variations is like primitive here. Here A not equals to B not equals to C and alpha not equals to beta not equals to gamma not equals to 90 degree. So all three angles and all three axial distances are different here, and the basic difference between orthorhombic and triclinic here. In case of orthorhombic, again axial distances are not equal like triclinic here, but in case of orthorhombic the axial angles are equal but not equals to 90 degree, but here for triclinic all angles are different and they are not equals to 90 degree. So this is the difference between orthorhombic and triclinic. So considering all possible variation, there are 14 different lattices are found. These are called 14 Bravais lattices. Okay. It can be seen that all lattices are not simple or primitive. On the basis of position of lattice points, it can be divided further. For cubic, we know that this is A equals to B equals to C and alpha equals to beta equals to gamma equals to 90 degree. So these are all, P stands for all primitive lattice here, I stands for body centered here, F stands for face centered, C stands for side center here. Okay. So there is one more C here and one more P here. Okay. Now for simple or primitive lattice, it has lattice points on every corner of unit cell. Okay. In case of body centered, so you see the primitive lattice. Okay. So in case of primitive lattice, it has lattice points on every corner of unit cell. So this is the unit cell. You see every corner of unit cell, you have the lattice points here, right? In case of primitive. For body centered, it has points at the corners as well as the body center of the cube. So I stands for body centered. You can see the lattice points are at all corners as well as at the center, okay, body centered here. Next comes face centered, okay. So it has points at the corners as well as at the corners of each face. So you can see this is face centered. So all corners you have lattice point, and you see in between each face, this is one face here. So in between that there is one lattice point. This is another face here. So you can see another point. This is another face, another point, and this is another face. You get another point here, okay. And for this one also you get another point here. So for face centered, it has points at the corners. All the corners are occupied, as well as at the center of each face, okay, center of each face. And last one is end centered. So it has points at the corners as well as the centers of any two opposite faces. So this is end corner or side corner, we can say. So here you can see the opposite faces, they have this. All corners are occupied as well as the centers of any two faces of two opposite faces. So this is one face, this is another face. So two opposite faces, you can see the points are here. Okay, so for, and then we discuss cubic. Okay, so cubic, tetragonal. Okay, so cubic is alpha equals to beta, a equals to b equals to c, and alpha equals to beta equals to gamma equals to 90 degrees. So all these things we discussed before. Now number of atoms per unit cell. From figure B, okay, it is clear that lattice points at the corners are shared by 8 unit cells. Each points at the faces shared by 2 unit cells, and points at body center belongs to unit cell completely. Okay, so thus the contribution of each atom to the unit cell is at corners 1 by 8, because all corners are occupied, 8 corners are there. Okay, so at corners 1 by 8, at faces half, okay, because each points at the face shared by 2 unit cell. Okay, so these are the faces, so each face is shared by 2 unit cells. Okay, so at face half, and within the body you get 1. Okay. Now considering the contribution of the lattice points, total number of atom per unit cell will be, so for simple cubic, so number of atoms at the corner, so 8 corners and 1 by 8, so you get 1. Number of atoms at the face, so there is no atom at the face here. You can see this is the if you consider this is cubic one, so you see there is no atom at the face. Okay. So 0, number of atoms at the body also 0, so total is 1. For body centered, if you see the body centered here, so these are the body centered. Okay, so we have 8 corners, so each occupied by, so 8 times 1 by 8, we get 1 here. Number of atoms at the face, there is no atom at the face, but only 1 atom at the body. You can see it here, 1 atom at the body. So you get 1 plus 1, so you get 2 here, right? And for face centered cubic, 8 corners are again occupied, so each one, so 8 times 1 by 8, so you get 1. So number of atoms at the face, so we can go back and check the face centered one. So this is the face centered one. Okay, so for each face we have 1 site occupied. So how many faces are there? 1, 2, 3, 4, right? So 6 faces are there, so you get 6 times 1 by 2 equals to 3, so total we get 4. Now macroscopic property of solid, so calculation of density. How we will calculate density? Consider a cubic unit cell of edge length A. So we are considering a cubic unit cell of edge length A centimeter. So volume of the cell will be A raised to the 3 centimeter cube. So the density of unit cell is mass of the unit cell by volume of the unit cell. Now mass of the unit cell, what will be the mass of the unit cell? So number of atoms in unit cell times mass of each atom. So we can write Z times M. So mass of an atom present in the unit cell will be, if we say M is atomic mass by Avogadro number. So you get M by Na, right? So the mass of the unit cell will be Z times M by Na. So if we substitute this in equation 1, okay, so we write density will be Z times M by Avogadro number times A raised to the 3 grams per centimeter cube. Okay. Next we discuss close packing in crystals. Close packing is an arrangement of particles where maximum spaces are occupied, leaving maximum void. So, 3-dimensional close packing can be built step by step. Okay, so 1-dimensional packing is in this arrangement, spheres are placed in a single horizontal row touching each other. So, this is 1-dimensional packing. This is very easy to understand. Okay. So, in this arrangement, spheres are placed in a single horizontal row touching each other, right. So, this is 1-dimensional close packing. So, the number of nearest neighbor of a sphere is called coordination number. Here the coordination number is 2. So, if you consider any sphere here, so suppose we consider this sphere. So, we have one sphere here, this is 1-dimensional only, and another sphere is here. So, the coordination number is 2. So, for each sphere we get 2 adjacent spheres, we get number is 2 here. Then we discuss 2-dimensional packing. So, it can be generated by placing multiple rows in different ways. First is square close packing or AAA type arrangement. In this type arrangement, spheres are exactly on top of each other. Spheres form a square, therefore, this type of arrangement is called square close packing. So, this is shown here, okay, square close packing here you can see. Okay, so if you see we are putting, this is the sphere, we are putting at top of this one another sphere A. For this sphere we are putting another sphere here. Okay, 2-dimensional. So, this is 1-dimensional, this is another dimension, 2-dimensional this is one is okay. Then we discuss hexagonal close packing or ABAB like this. So, type of arrangement, ABAB type of arrangement. In this type of arrangement, the second row is placed in the depressions of the first row, third row is placed in the depressions of the second row, and so on. Okay, so if we consider this one, okay, so A and then B and then again A, so there is a depression and then again B like this. Okay, so this is hexagonal close packing. Now, from the image itself, it can be easily said that the hexagonal close packing is more compact than square close packing, leaving space. So, there is less space here, you can see, okay, very less space between here. Okay, so you can get hexagonal like of this, and this is your square. Okay, square close packing. You can see a square here, you can see a hexagon here. Now, you can see the space between here is is less compared to square close packing. Okay, so that's why the square close packing with packing efficiency is 52.4%, whereas for hexagonal close packing the packing efficiency is 60.4%. Okay, that's what. So, from this image itself, it can be easily said that the hexagonal close packing is more compact than square close packing, leaving less space. The coordination number for square close packing is 4 and for HCP it is 6, right. So, for if you consider this atom, so how many atoms are adjacent to this one? 1, 2, 3, 4, 5, 6. You consider this one 4, right. Okay, so that's why the coordination number for SCP means square close packing is 4, whereas the for HCP, okay, the coordination number is 6. Then we move to 3-dimensional packing. 3-dimensional packing from square close packed layers. The second layer is placed exactly above the first layer. So, spheres are placed perfectly both horizontally and vertically. This type of arrangement is called A type or simple cubic packing. So, in 1 dimension we have like this, 2 dimension we have like this. Okay, this is 2 dimension thing. Now, 3 dimension we have like this, this and this. Okay, so 3 dimension is 1, this is 1 dimension, this is 2 dimension, this is 3 dimension. This is 3-dimensional close packing thing. Okay, so 3-dimensional packing from hexagonal close pack layers. So now we discuss voids. In the first layer, say A, there will be empty space called void. In the bottom image, it is clear that there are 2 types of voids mentioned as A and B. You can see void A here and void B here. Okay, this is 3-dimensional thing, is difficult to understand. So, okay, in layer B, is placed on top of void B and A will be unoccupied. Okay, so layer B is placed on top of void B, right, here, and A will be unoccupied. So this space is unoccupied here. The C type of voids are triangular, but A type of void of the second layer are a combination of two triangular voids. Whenever a sphere of second layer is placed above the void of first layer, a tetrahedral void is formed. Void C represents tetrahedral void. The triangular void of second layer is above the triangular void of first layer, and the two triangular do not overlap. Such voids are surrounded by 6 spheres and called octahedral void. Void A represents octahedral void. So here void A is called octahedral void. Then we discuss hexagonal close packing. Here the third layer lie directly those of first layer, that is the first and third layers are identical. This type of arrangement is called ABA, AB, like A, like this arrangement, or hexagonal close packing, or HCP. In this type of arrangement, third layers of spheres may be placed on the tetrahedral void C, for example magnesium, beryllium, zinc, etc. Then we discuss cubic close packing. The third layer is placed over octahedral void and a new layer labeled as C is formed. In this type of arrangement, fourth layer will exactly the same as first layer. This gives an ABC type of arrangement, or cubic close packing, or CCP. So here you can see the octahedral void is shown here, then tetrahedral void is shown here. This is the example of HCP, this is CCP, this is hexagonal, this is cubic, and this is cubic close packing, how it looks like that. So ABC like this, and for hexagonal AB like this. Okay, so now we discuss packing efficiency. Packing efficiency is the percentage of total space filled by the particles. In cubic close packing or face centered cubic arrangement, suppose length of the edge of a unit cell is A and radius of each sphere is R. So number of spheres per unit cell in face centered FCC is 4, right? So you can see it here. Okay, so from the figure it is clear that AC is 4R. If you consider AC here, so this is R radius, this is diameter 2R, and this is R. So this is 4R, right? AB is A. So AB, if we consider this one, AB is A, and BC is also A, right? Here BC is also A. Now since ABC is a right angle triangle, now if you consider ABC, this is a right angle triangle, so AC square will be AB square plus BC square. Now AC, value of AC is 2R, AC is 4R, so 4R whole square, and AB and BC both are equal, right? So you get A square here plus A square here, so we get 2A square. So from there we can calculate the value of A. So value of A will be 2 square root of 2 and then R. Now what is the volume of the unit cell? So volume of this unit cell is A to the A raised to the 3. So what is the value of A? We just got the value of A is 2 square root of 2 times R. So AQ gives 2 square root 2 times R raised to the 3. So we get 16 root 2 R to the 3. So total volume of 4 sphere. So for each sphere the radius is R. Okay, so volume of one sphere is 4 by 3 pi r cube, right? And we have how many spheres are there? 4 spheres are there. So we get 16 by pi r cube. Okay, so what will be the packing efficiency? So packing efficiency will be volume of the 4 spheres in the unit cell by total volume of the unit cell times 100. So total volume of the 4 sphere we just calculated, right? 16 pi r cube by 3, and volume of unit cell we all calculated 16 square root 2 r to the 3, so times 100. So if we calculate this, we get the packing efficiency 74%. In body center cubic arrangement, or BCC, suppose length of the edge of unit cell is A and radius of every sphere is R. So number of spheres per unit cell in BCC is 2. So length of the body diagonal is root over square root 3 times A. So for BCC, 4r is square root 3A. So A will be 4r by square root 3. So volume of the unit cell, like before, we can calculate 8 raised to the 3, and the value of A we just calculated 4r by square root 3. So that to raised to the 3, so we get 64r raised r to the 3 by 3 root 3. Now total volume of two sphere. So for one sphere, volume is 4 by 3 pi r cube. So times 2, because the total volume of two sphere is 2 times 4 pi r cube by 3. So we get 8 pi r cube by 3. So packing efficiency, again volume of the two spheres in the unit cell. So what is the volume of the two sphere unit cell? That is your 8 pi r cube by 3. And total volume of the unit cell is this one, 64 r cube by 3 root 3 times 100. So we get 68%. So what we found? We found that in cubic close packing or face centered cubic arrangement, the packing efficiency is 74%, whereas in the BCC arrangement, the packing efficiency is 68%. Third one is in simple centered cubic arrangement or BCC arrangement. Suppose the length of the edge of a unit cell is A and the radius of every sphere is R. So number of spheres per unit cell in SCC, this is SC, it is simple cubic cell, not BCC. Okay, so in SCC it will be 1. Okay, so since two spheres are touching each other along the edge AB, so you see two spheres are touching each other along the AB. So what the length of AB is r plus r, 2r. So we get 2r. So that is your A here, right? This is your A. So volume of the sphere, again 4 by 3 pi r cube, and volume of the cube will be A to the raised to the 3, and the value of A is 2r. So we get 8 r cube. So the packing efficiency, again like volume of the sphere in the unit cell. Okay, so by total volume of the unit cell times 100. So volume of the sphere in the unit cell is 4 by 3 pi r cube, and total volume of the unit cell is 8 r cube times 100. We get 52.4%. Next we discuss atomic radius. So atomic radius is the distance from the nucleus to outermost shell of electrons. What is ionic radius? Ionic radius is the distance from the nucleus of an ion up to which it has an influence on its electron cloud. So important generalization, the radius of a cation is less than the radius of its parent atom as one electron is removed from the outermost shell. And the radius of an anion is higher than the radius of its parent atom as one electron is added to the outermost shell. Then we discuss radius ratio rule. In ionic solids, the anions usually occupy closed packed arrangements and cations usually occupy void. This is very important thing. Okay, so in ionic solids, the anions usually occupy closed packed arrangements and the cations usually occupy void. Radius ratio is a tool to predict whether the cation will occupy TD or tetrahedral or octahedral void. The number of oppositely charged ions surrounded each other is called coordination number. So the radius ratio is the ratio of radius of the cation to the radius of the anion. So radius ratio will be radius of cation by radius of anion. So r plus by r minus.